Hello dear students of grade 11, you are welcome in our new mini lecture, and today we're going to study the section 1 and chapter 3. Actually the whole chapter is about the physical characteristics of gases, the whole chapter, chapter 3. In section 1 we're going to study the kinetic molecular theory about gases. Okay, so I have section 1 here. Section 1 is the kinetic molecular theory of matter first. Later we'll talk about gases and details of gases. What is kinetic molecular theory? Kinetic molecular theory. It is a theory that explains the properties and behavior on matter on the principle or the base that says the particles are in motion. Particles are in motion. Particles of gas are in motion. Particles of liquid are in motion. Even particles of solid are in motion. How they are in motion? They vibrate on fixed positions. Sorry, it looks there's a problem here. Okay, let's be back. We said that even the particles of solid, such as this marker, they vibrate on fixed positions, which means they are in motion, but their motions are limited in range. Okay, so. Now we have the kinetic molecular theory of gases. This theory, the KMT, kinetic molecular theory, explains the properties and behavior of gases on the principle that we say that they are in motion. So we have first we need to study the assumptions. Before we study the assumptions, this theory is being applied on what? On ideal gas. This theory is being applied on ideal gas. What is ideal gas? It is an imaginary gas. Imaginary gas, which means the gas in our daily life, the gas that inhale, we exhale, the gas we use in industry. These are not ideal gases. These are real gases. What is ideal gas? The ideal gas is the gas that fits with the assumptions here, the assumptions of kinetic molecular theory. So ideal gas is an imaginary gas that fits with the 5 assumptions of kinetic molecular theory. Let's see what we have in these assumptions. Assumption 1 says that the gas particles, or the gas consist of a huge number of particles, and these particles are far apart from each other relative to their sizes, which means their sizes are very, very, very small, and the distances might be between two particles. An average might be about 10,000 as the size of the gas particle. So we can see here in this figure. Okay, this is of course magnified view for the gas particles. We see the gas particles are far from each other, are distant from each other. Of course, the distances here can be wider relative to the size, but this is just for explanation, illustration. So the first assumption is gases consist of a huge number, large number of particles that are far apart, and the distances are very wide relative to their sizes. Okay, let's move to the second assumption. The second assumption, of course, when these particles are in motion, they collide each other and they collide the walls, which means the particles collide each other here. The particles here collide each other, and also they collide with the walls of the container. These collisions are elastic. What are elastic collisions? Which means the collisions that do not cause loss of kinetic energy, which means they collide each other, but their kinetic energies are constant as long as the temperature is constant. As long as the temperature is constant, the average kinetic energies of gas particles are constant. This is assumption 2. Let's move to assumption 3. And assumption 3 says that gas particles are in constant rapid random motion. Constant rapid random motion, which means they keep on movement, and this movement is fast because they are gases. And this movement has no specific direction. They move in all directions. they move in all directions. And this assumption 3, and the assumption 4 accounts for many properties and characteristics of gas. We will see later. So assumption 3 says that gas particles are in continuous random motion in all directions. As we saw here, they are in motion, so they collide against each other, they collide against the wall, but the collisions are elastic, do not cause loss of kinetic energy. Assumption 4 of KMT, kinetic molecular theory. There are no forces of attraction. There are no forces of attraction among the gas particles or between the gas particles. Why? Because the kinetic energies are relatively high. So the kinetic energies of particles overcome the attraction forces. The higher the kinetic energy, the lower the attraction forces. Let me repeat. The higher the kinetic energy, the lower the attractive forces. So because the kinetic energies of gas are high, the attraction forces or the attractive forces are low, so they don't attract each other. The attraction reached zero. This is the fourth assumption. The fifth and the last assumption is the average kinetic energy of particles of gas, the average kinetic energies of the particles of gas directly proportional to temperature, which means they depend on temperature. So if you have a water vapor, for example, at 50 Celsius, and we have water vapor at 150 Celsius. Of course, the particles of water vapor at 150 Celsius will have much greater kinetic energies than these of water vapor at 50 Celsius. So it depends. The kinetic energy average depends on the temperature. And we have the very famous equation of Einstein. This very famous equation of Einstein that he used to calculate the kinetic energy of any object. Of course, the particles are objects despite their being tiny. Here it says the kinetic energy of any particle equals half mass times square of velocity. Half of mass times square of velocity. Okay, we said that the kinetic energy depends on temperature. So suppose that you have two gases at the same temperature. The particles will have the same average kinetic energies, but one of them will have higher mass, higher molar mass or higher molecular mass than the second. So the one with higher molar mass will have velocity less, which means slower. They move slower. Kinetic energy is constant. Mass is higher, so velocity is slower. And the opposite to the gas that has lower molar mass. The same kinetic energy, lower mass, higher velocity. This is what we will talk about in next sections, in coming sections. Don't worry about it now. Okay. So we said if you have two gases at same temperature, particles having equal kinetic energies, so the heavier has a slower movement. The heavier, suppose that you have CO2 and H2 gases. CO2 has molar mass of 44 gram per mole. H2 has a molar mass about 2 gram per mole. So which one moves faster? Of course, hydrogen. If you have two persons, one weighs over 100 kilograms and the second weighs 60 kilograms, of course, the fit one can run faster. This is also applied for gases. The gases with smaller molar mass under same conditions move faster. Okay, so these are the assumptions, and now let's study the characteristics or nature of gases and explain them based on the assumptions of kinetic molecular theory. The first one, expansion. Gases can expand, which means gases can occupy the volume of the container they put in. If the container is a balloon, if the container is a tire, if the container is this room, so gases expand. Why gases expand? Assumptions 3 and 4 counts for this. What do these assumptions 3 and 4 say? Assumption 3, what does it say? it says the gas particles are in continuous random motion in all directions. 4, it says no attraction forces among them. So no attraction forces and free movement, of course, they expand. Of course, they expand. Okay, this is, but first you must know what is expansion. Expansion is what is the ability to increase volume or to occupy volume of the container. 2, we have a fluidity. Maybe students of mechanical engineering deal a lot with the fluids. Fluids, a term, fluids is a term describes gases and liquids. Fluids, a term that describes gases and liquids. Why gases and liquids? Because they can flow, because they can be moved from a container to another container. So gases and liquids are what? Are fluids. Gases and liquids are fluids. Why gases can flow? Why gases can flow? Why gases can be easily transferred from a container to another container? Also assumptions of 3 and 4 count for this. Assumption 3 says the particles are in continuous random motion. And assumption 4, no attraction forces. So they can freely move from a container to another container. This is the second characteristic. Let's move the third characteristic, which is low density. Gases are light. Gases have low densities. Gases have about 1 out of 1,000 of density of their corresponding liquids or even solids. Why they have such low densities? Assumption number 1 counts for this. Assumption number 1 says, let's be back to assumption number 1 and see what does it say. It says that gas consists of large number of particles and they are far apart from each other, far apart. So the farther, the lower density. Okay, so this is the low density and assumption number 1 counts for this. 4, we have compressibility. Compressibility is opposite of expansion. Compressibility is the ability to reduce volume under pressure. If you have a balloon and squeeze it, wouldn't it reduce volume? Of course it would. And also we have the piston here. We have a piston here, it's a car piston, a car engine piston. Here, sorry. Here the pressure is low, but here the pressure is high. So the volume is reduced by what? Under pressure. So gases can reduce volume, can decrease volume under pressure, and this is called compressibility. What counts for this? Also assumption number 1. Assumption number 1 says that they are far apart. So under pressure, these distances can be reduced, can be minimized. So volume can be reduced. That's why they are compressible. Which assumption counts for this? Assumption number 1. And finally, we will talk about diffusion and effusion. Diffusion and effusion. What is diffusion and what is effusion? Something diffuses. Something can, let's say, can move freely. Actually, diffusion is the spontaneous, freely. Spontaneous mixing of two substances, maybe more. So if somebody opens, unlocks the gas tap in the kitchen, and you're sitting in the living room, you can smell it. Because the gas can flow, the gas can diffuse. The gas, propane gas, mixed freely with oxygen and nitrogen until it reached you and you could smell it. So this is the spontaneous mixing of two substances or more. The question here is, only gases can diffuse? Can fluids diffuse? Can liquids diffuse? Can solids diffuse? Of course they do. Liquids also diffuse. Solids diffuse, but on long term of time, which means solids are slower in diffusion. Gases are the fastest in diffusion. Which means faster than liquids, faster than solids. Okay, now what counts for diffusion? Let's first have a fusion also, and have the reasons. We have diffusion, we just talked about it. Sorry. Okay. We have diffusion, and let's talk about effusion. You know, most of people think that the solid substance is not having openings. So for example, this marker, it looks to have no opening, but actually there are microscopic opening through any solid substance. The gases can move, can transfer through these tiny openings, through these microscopic openings under pressure. Under pressure, they can effuse. So what is effusion? Effusion, as written here, passage of particles through tiny openings under pressure. Diffusion was spontaneous, but here it's under pressure. So how can they effuse and diffuse the gases? Also, the assumptions of 3 and 4 account for this, because they are in constant random motion, because they don't attract each other. And here we have actually one small note about effusion and diffusion. Let's have a look at here at the figure. In this figure, we have two gases. We have nitrogen gas, which has molar mass, We have nitrogen gas, which has molar mass of 28. Each atom of nitrogen, 14 and 14, 28. And we have also hydrogen gas, which has molar mass of 2 grams per mole. So which one is lighter? Of course, it's hydrogen. Which one is heavier? Of course, it is nitrogen. Which one effuses or diffuses faster? Because the tab here is not a tiny opening, it's a big opening. Okay, you can see that they could diffuse. It's a spontaneous mixing. But actually, if it related to effusion and diffusion also, the gas with a smaller molar mass would effuse and diffuse faster under the same temperature. Okay, now you can see here in the figure, gases diffuse readily into one another. The space between the molecules allow different gases to mix together easily. So the particles are not stick to each other. They are not packed. They are free. The distances are wide. So you have assumption 1, assumption 3, assumption 4. All counts for the ability of diffusion and effusion. These are the characteristics of gas, and we explained them. We counted for them based on KMT, kinetic molecular theory. Now let's see what about the gases in our daily life. So far we talked about the ideal gases that fit 100% to the kinetic molecular theory. What does the term real gas mean? We have a real gas here. All gases in our life are real. But many gases show behavior close to ideal gas, especially under low pressure and under high temperature. Let's have a look on this piston. This piston, here the pressure is low, and the particles are apart from each other. And in the second, in B, we have the piston is pushed down, so the particles are closer. The kinetic energies here are higher, the kinetic energies here are lower. So we have here low pressure, we have here high pressure. Low pressure, high kinetic energy, low kinetic energy. In which case the gas here in the piston behaves closer to ideal gas. Of course it is here. Here is closer to ideal gas, closer to ideal gas. Why closer to ideal gas? To ideal behavior? Because they are apart from each other. The attraction forces are the least, the kinetic energy highest. So under low pressure, most of the gases, the real gases, behave ideally or very close to ideally. Okay, now, of course, there is some deviation. The deviation is counted by van der Waals. There's Johannes van der Waals. He asked himself why real gases deviate from behavior of ideal gas, and he suggested two reasons. Because the reason number one, the gas particles occupy volume. Actually, in assumption 4, I missed to tell you that gas particles, according to kinetic molecules, they do not occupy a volume, and also they do not attract each other. So we have no volume occupied and no attraction force. Here, Van der Waals says the first reason of deviation of real gas from ideal behavior is particles occupy volume. Second, they exert attractive forces on each other. So these two reasons justifies the deviation of real gases from ideal behavior. Which gases that good candidates to behave as ideal gases? The nonpolar gases, especially nonpolar gases with monatomic molecules such as helium and neon. Okay, we have helium and neon here. Helium is a noble gas, neon also a noble gas, and both have monatomic molecules. So under low pressure, these two gases are very close to ideal behavior. Also, we have other gases, diatomic, but what? But nonpolar. Also, they can, under low pressure, they can behave close to ideal gases. Which gases deviate more or show significant deviation from the ideal gas? The gases that have polarity, which means the polar gases, such as what? Such as water vapor, H2O, HCl, NH3, ammonia, hydrogen chloride, water. So under which condition, the water vapor, because it's polar, it shows a greater deviation from ideal gas. NH3 also polar. Also, it shows significant deviation from ideal gas. Okay, under which conditions these gases show behavior close to ideal gas? Under high temperature and low pressure, or low pressure and high temperature. Why? Because the kinetic energies are high and overcome the attractive forces between the gas molecules. That's all about this section. Let's have a look on the section review, and the questions are pretty easy actually. So actually I put the questions to left and in the front of them the answers. Number 1 says use the kinetic molecular theory to explain each of the following properties of gases: expansion, fluidity, low density, compressibility, and diffusion. First, we have the expansion, compressibility, diffusion, and fluidity. We talked about them. The assumptions 3 and 4 account for this. The particles are in random motion. The particles do not attract each other. The particles do not occupy volume. So, expansion, compressibility, fluidity, and the other one, the diffusion. Of course, diffusion and diffusion is reasoned by assumptions 3 and 4. What about the other one we have here? Assumption 3 and 4. Okay, the low density. What about the low density? Low density is reasoned by what? Or explained by the assumption number 1. The particles are far apart. So, of course, the gases will have low densities. Okay, the question number 2 says describe the conditions under which the real gas is most likely to behave ideally. Under low pressure and high temperature. Why? Because the kinetic energies are high and they overcome the attractive forces among the particles. Question 3. Which of the following gases would you expect to deviate significantly from ideal behavior? We have helium, not. It is fit. O2 is nonpolar. Of course not. H2 is nonpolar. Oh, we have H2O here. H2O is polar, very high polarity. So this is expected to have big deviation from ideal gas. And we have HCl also polar, NH3 also polar. So the last three, water vapor, hydrogen chloride, and ammonia. Water vapor, hydrogen chloride, and ammonia show significant deviation from ideal gas. Why? Because they are polar. They attract each other. The particles attract each other. Okay, and finally we have question 4. How does the kinetic molecular theory explain the pressure exerted by gases? Okay, the assumption 3 says that the particles of gas are in constant, random, rapid motion. Of course, this motion exerts force on the walls of the container in all directions. And we know that the pressure is amount of force exerted on unit of area. So we have a force and we have area. Of course, there will be pressure. So assumption 3 counts for the pressure exerted by gas particles on the walls on the container. That's all about today's mini lecture. I wish you get benefit from it and wish to meet you on next mini lecture. I wish you having a nice day.